Now we are going to discuss the behavior of the analog systems in presence of noise. To understand this, first we will consider the baseband system. Baseband system means without any modulation, if I want to transmit and receive, how the system will behave. So consider the model. Noise is added. We have the receiver and the output is SO and NO, and corresponding time domain representation may be like this. So this is the model that we are going to use. This one is the transmitter. Transmitted signal is ST. Then channel. Then we have in the channel some noise is added, and finally we have the receiver. Input to the receiver is SI and NI, signal part and noise part. And the output is S0 and N0, signal part and noise part. MT is the baseband signal, which is zero mean wide sense stationary random process, and it is band limited to B Hz. Now we shall consider the case of ideal low pass filter for the baseband with bandwidth B at the transmitter and also at the receiver. Now the channel is assumed to be distortionless. Now for this case, S0 equal to SI, SO equal to SI, and N0 or NO equal to 0 to B Sn omega dF, where Sn omega is the power spectral density of the channel noise, and here we are assuming this channel noise is a idealistic noise of white Gaussian noise. So Sn omega is n by 2. This is the power spectral density. So NO can be written as 2 0 to B n by 2 dF equal to n into B. So N0 is this, S0 is this, so we can calculate the output SNR. S0 by N0, that is equal to SI divided by N into B. Now we define a parameter gamma equal to SI divided by N into B. So that is equal to S0 by N0. Output SNR of this baseband signal is gamma, and we will try to understand the DSB-SC and SSB-SC performance with the help of this parameter. Now we are going to consider the DSB-SC system. MT is the baseband signal. We have a product modulator to generate the DSB-SC. This is the transmitter part. Then we have the channel. In the channel we have, this is the channel portion, and in the channel some noise is added. Now at the first stage we have a band pass filter at first stage of the receiver, and after band pass filter we have SI-NI as a signal and noise part of this. In the frequency domain we are writing SI and NI, and signal power and noise power, they are represented by SI and NI, and YIT is the input signal. Now this part is actually the demodulator part, this section. This is the demodulator section. We have a synchronous detector, so it will be multiplied by √2 cos omega ct. Then we have a baseband filter, and the output signal power and noise power are this, and YOT is the output signal. Now in this case, SI can be written as m square t bar. This is the input signal. Next, YIT can be written as √2 mt cos omega ct, that is the DSB-SC, plus NT. NT is added here. Now after passing it through the bandpass filter, it becomes narrowband. This NT becomes narrowband. So YIT should be written, we should write YIT in terms of its quadrature component, that is √2 mt plus NCT into, in phase component is NCT cos omega ct plus NST sin omega ct. NST is the quadrature phase. So writing, being this noise becomes narrowband, we can write this noise in terms of narrowband, conventional expression for narrowband noise with in phase component and quadrature component. Now this signal is now multiplied with √2 cos omega ct, and then low pass filtered. So the higher frequency terms will be eliminated by this baseband filter. So YOT will be MT plus 1 by √2 NCT. So SO equal to m square t bar, that is equal to SI, and N0 equal to half of NC square t bar. Now assuming the white noise, the power spectral density is n by 2, so we can write NC square t bar, that is equal to n square t bar equal to twice n b. So N0 equal to n into b. So output SNR can be written as 0 by N0 psi by n into b, that is equal to gamma. That means for fixed transmitted power, the SNR at the demodulator output is same that for the baseband signal. That means DSB-SC performance and baseband performance are identical. And so this is the performance of the DSB-SC synchronous detector. Now let us consider the case of SSB-SC. In this case, the system may be drawn in this way. MT is the baseband multiplied by 2 cos omega ct produce DSB-SC, and then we have the sideband filter, single sideband filter to produce SSB. So this part is the transmitter. So in the channel, this section is the channel, some noise will be entered. Now we have a bandpass filter, and that band pass filter, we are assuming that this SSB-SC, we are keeping this LSB only. So we have a band pass filter. The output signal and noise are SI and NI, and the signal is YIT. So this section is the demodulator part, synchronous demodulator multiplied by 2 cos omega CT, and then we have a baseband filter, and the output is signal power and noise power, and YOT is the output signal. Now the SSB signal can be written in this way: MT cos omega CT plus MHT sin omega CT, where MHT is the Hilbert transform, and SIT, the signal power, input signal power, is M square bar. Now since after passing it through a narrow band pass filter, this NT becomes narrow band, so we can write this NT in terms of in phase and quadrature component. So YIT can be written as MT plus NCT cos omega CT plus MHT plus NST sin omega CT. This signal is now multiplied with 2 cos omega CT, and then we are passing it through the baseband filter. So baseband filter will remove all the higher frequency terms, and the output signal can be written as MT plus NCT. So the signal strength at the output is M square T, M square bar, that is equal to SI, and N0 equal to NC square bar. Now assuming we have only lower sideband, so N0 equal to NC square bar, that is equal to N into B. So SNR can be written as output SNR, SO by NO, that is equal to SI by N into B, that is again equal to gamma. That means performance of SSB-SC as well as DSB-SC, the performance are almost identical in terms of resource utilization. Now we will consider the coherent demodulation of AM. Since it is a coherent demodulation of AM, this circuitry or the model will be same as that of the DSB-SC. Only thing is that along with this DSB-SC we have some carrier A cos omega CT. So that's the only change. So same model is useful right here. So in this case, the received signal is √2 into A plus MT cos omega CT, and at the receiver we will multiply this signal with √2 cos omega CT, multiply by √2 cos omega CT. So we will get the demodulator output MT after multiplying and after passing it through a baseband filter. So SO equal to M square bar. The output noise is also same as that of the DSB-SC. Now as received signal is √2A MT cos omega CT, under this condition SI can be written as √2 square into A plus mt square bar divided by, sorry, this square plus this square plus that square into half due to this cosine term. So that is equal to A plus mt square bar. So SI equal to A square plus m square t bar plus 2A mt. Now mt is assumed to be 0 mean. That means SI equal to A square plus m square t bar. So output SNR is this, that can be written as m square by A square plus m square bar SI, same thing, divided by n into d. This one is gamma, so m square bar by A square plus m square bar into gamma. Now if maximum value of mt is say mp, then A must be greater than equal to mp. That is the primary condition for AM. So for the maximum SNR, A equal to mp, that means when modulation index equal to 1, and under this condition SO by NO maximum is m square by mp square plus m square bar gamma, that is equal to 1 by mp square by m square bar plus 1 into gamma. Now as mp square by m square bar is always greater than or equal to 0, so SO by NO will always less than equal to gamma by 2. So maximum value is gamma by 2, and in general it is less than gamma by 2. That means the performance is inferior. So the performance of AM is inferior compared to the DSB-SC or SSB-SC. So performance is worse, rather. Performance is worse for this case. So far we discussed is the performance of AM for synchronous detection. Now let us consider the envelope detector. envelope detection. Here the received signal A plus mt cos omega ct the demodulator signal, demodulator input yit, we have to first calculate yit is A plus mt cos omega ct plus the channel noise. Using quadrature component representation of nt, we have yit A plus mt plus nct cos omega ct plus nst sin omega ct, where nct is the in phase component and nst is the quadrature component. The desired signal at the demodulator input is A plus mt cos omega ct. So the signal power SI equal to A plus mt square bar divided by 2, that is equal to A square plus m square bar by 2. Now rewriting this yit in polar form. So yit equal to eit cos of omega ct plus angle theta I t. And the envelope eit, that is equal to A plus mt plus nct whole square plus nst whole square. So this is the envelope. An envelope detector should detect this signal. So now we have two cases. One is the small noise case, another is the large noise case. So first consider small noise. Here A plus mt signal part is much greater than noise part. So obviously A plus mt will be much greater than nct as well as nst. So we can write eit approximately A plus mt plus nc t. This part will be neglected, this nst. So output signal strength is m square and the output noise is nc square bar, that is equal to twice n into b, twice n into b. So S0 by N0, output SNR, that is equal to m square bar by a square plus n square bar into Si by n into b, that is equal to m square bar by a square plus n square bar into gamma. So this one is same as that of the synchronous detection. Same as synchronous detection, but the condition is here we have small noise case. That means when the noise is small, then its behavior will be same as the synchronous detection. Same as synchronous detection. Now we will consider the second case, condition 2, that is the large noise. Large noise. In this case, n is much greater than a plus mt. So obviously nct or nst will be much greater than a plus mt. So under this condition, the envelope EIT can approximately be written as ns square t plus nc square t plus twice nct into a plus mt, and the square of this term will be neglected since this one is very small. So that can be written as ENT square root of 1 plus 2a plus mt ENT cos of theta t, where ENT is the envelope and this theta is the phase of the noise NT. So ENT is equal to NC square plus NSS square, and theta you can write it at theta n. N stands for noise. Theta nt equal to minus tan inverse nst by nct. So nct equal to nt cos theta nt and nst equal to ent sin theta nt. And since ent is greater than a plus mt, so EIT can be approximated as ENT 1 plus A plus MT divided by ENT into cos of theta nt. That means ENT plus A plus MT cos theta nt. That means MT is now mixed with theta nt, which is the noise part. That means MT is completely mutilated completely mixed with noise, so recovery is not possible. That means when signal to noise ratio for large noise case, recovery is not possible. For small noise case we can recover. That means at a certain SNR, the receiver stops working. This is called the threshold effect. So envelope detector shows the threshold effect, and that is the basic problem of this envelope detector.